You can start, Anton.
Okay, good afternoon, ladies and gentlemen. It's a pleasure to welcome you to this webinar, Boosting Hydropower, Best Practice for Research. So in principle, it's the 5th edition, and we are again happy today to have a presentation of 3 ongoing European research projects which concern hydropower. So I will guide you briefly through the agenda, please, Uriah. So as I said, we have 3 projects which will be presented today, Hydro4U, Alphas, and Hypos. So we can go to the next. As usual, I make a very brief introduction to ATP hydropower, what is ongoing in our, let's say, project. Next one. So you can go the next one. So the last 2-3 years, a lot of, let's say, things have changed in the environment. So everybody knows we had a difficult time after the war in Ukraine started, so which revealed really that hydropower has to play an important role in the safe energy supply, electricity supply in Europe. We have also seen last November a very important Dunkelflaute event in Europe. So we have also seen there that storage and pumped storage hydropower are very vital to avoid or to help to avoid such blackouts. What very positive we see also, there is a kind of renaissance of hydropower in Europe. At the moment, 9,000 megawatt to 12,000 megawatt projects are under planning. And you remember well, we had recently a blackout event in Spain and Portugal. And of course, hydropower was not involved in that blackout, but hydropower was very useful or was even necessary to restore afterwards the grid again, because hydropower can function in a black start mode. So the next one, Raya. You can click 2 or 3 times. So this graph shows a little bit which country use how much hydropower and which is the potential which can be built if there is a basis in future. So I just wanted to show that all the countries which are indicated in with a star, they have a potential which is more than they have used today. If I'm talking of potential, it's in principle economical feasible potential, but we all know that there are other constraints to tap this potential. We just mentioned this blackout event in Spain and Portugal. You see that Spain has quite an important share of hydropower. So as I said, hydropower then played a very important role to restore the grid after this event. We can go to the next one, perhaps, Uriah. What is also a little bit positive, we see a slight increase of construction of hydropower in Europe since 2023. Before it was quite some decrease, and it seems that this increased activity in hydropower continues over the next years with a certain speed. Next one. You know ATP hydropower. In principle, it's based on the Hydropower Europe project, where we prepared 2 important documents, which is a research and innovation agenda and the strategic industry roadmap. And in principle, we in ATP Hydropower, we will consolidate the network which we built there, and we can go to the next one. So the intention of ATP Hydropower is to unify the sector, to present a kind of unified voice, because there are a lot of initiatives ongoing in the hydropower sector. Of course, we don't want to duplicate what is already existing. And we are, for example, also have a close contact with the European Hydropower Alliance. Next one, Ryan. Hydropower, ATP Hydropower is under action. So we have industry-driven governance in place with a lot of stakeholders. We have a scientific advisory board, 26 members. Chairperson is Dennis Albrecht. Co-chairs are Antonello Frigerio and Peter Stettner. And we have a very interesting online product, which is the HERI platform, where you can, in principle, discover ongoing research projects, but also information on research organizations. Next one. We are at the moment strongly working with 4 working groups. We have one on role for flexibility and storage, then hydropower and biodiversity, hydropower and climate change, and then a 4th group, which is organizing in principle these seminars, is the promotion, dissemination, and uptake of past and current European research and innovation projects. So we are well advanced with these working groups, and white papers will be published soon, before summer 2025. We have already some products. Next one. Yeah, that's all these working groups. They have also had the task to produce a short video, and this is a video which has been produced by the working group Flexibility, which you can discover on our website, but also on YouTube. It's a very nice film, I would say, showing a multiple people, cyclists, fighting for flexibility when driving, let's say, the electricity grid. Next one, Uriah.
Do I play the video or we keep?
Oh, I think we
Okay.
we want to have a little bit more, let's say, likes on the video, so that everybody can look it afterwards.
Okay.
Okay. So this working group who is organizing these webinars, one of the purposes is to disseminate the results of past and ongoing and planned European research projects on hydropower. And as I already said, we have today the 5th of this series of webinars. Next one, Uriah. Don't want to lose too much time. So in conclusion, you can find more information on our website, also LinkedIn and YouTube. You can see this nice flexibility film. Either you go on the website or you go on YouTube, you will find it. And if you are not registered in our consultation platform, please do so, because then you will get information regularly on any activities in the field of hydropower in Europe, but also worldwide. Next one. So we had, just to give you that information, we had a very successful hydropower day. It's the 3rd one we organized in April. And if you have not participated to that hydropower day, you can anyway find all the presentation on our consultation platform. So next one. So now we go into the webinar. I have the pleasure to announce the first speaker, Emanuele Quaranta. So please, Emanuele, the floor is yours.
Thank you, Anton, for the presentation. Thank you also, Iraya and Janire, for organizing this. I share my screen. Okay. Okay, can you see it? Because I cannot see you.
Yeah, we see it perfectly.
Yeah, just the full screen. Yeah.
Uh, okay, it's fine.
Yeah, it's fine. We can see it. Not full screen, but we
Okay.
see it.
If you find somewhere the full screen.
Maybe down on the right side, the page that is, I don't know if that's the icon, but if not, you can go like that. It's
Yeah,
you can
yeah,
see it,
okay.
everything.
You can see it.
Because I just installed the recent version of PDF and I cannot find.
Okay, so
full
let's
screen
say it's a PDF. Yeah, okay.
Yeah. Okay,
No,
so
no
thank you.
problem. We can
Yeah.
see it.
Yeah, thank you very much. I am Emanuele Quarante, the chair of the Transversal Group. I work at the Joint Research Center of the European Commission, in particular in the Ocean and Water Unit. The JRC, which is the acronym of Joint Research Center, is the scientific arm of the European Commission. We provide scientific support and evidence to the European Union policy-making process. And we also carry out our scientific researches to support this. Today, I will talk about recent policies and programs for hydropower. In particular, here you can see our unit, the Ocean and Water Unit, and we work in all kinds of water-related topics, from river to the ocean to water in agriculture, water energy nexus, hydropower, and so on. And we have contributed to develop several policies, like, for example, the Water Framework Directive or the Drinking Water Directive, the Flood Directive, and many others. So the first topic of today is related to the Horizon project. You know that the Horizon framework is that framework that finance technologies in Europe and beyond, in particular also on hydropower. As you can see in this picture, we in the last 10 years, we have had an average of 10 million euros per year funded in hydropower topics. In particular, in 2024, we had almost 20 millions of funding given to European Horizon project on hydropower. Today, there will be 3 projects, the Hydro4U, Alpheus, and Hypos. Hydro4U is focused on small hydropower in Central Asia, so also in order to improve the export capacity of European companies. Alpheus is focused on small hydropower and low hydropower for pump storage hydropower plants, and Hypos is more focused on digitalization and satellite processes. One interesting new policies that is not directly for hydropower, but where hydropower can fit well, is the recast Urban Wastewater Treatment Directive. This asks member states to reach at national level energy neutrality of the wastewater sector. So wastewater treatment plants should, aggregated at the national scale, produce the same amount of energy they consume. And in order to do this, there are not only opportunities for example, biogas or photovoltaics, but also for hydropower and small hydropower using the wastewater. So I encourage all the industry and hydropower operator also to contact the wastewater treatment operators in order to understand if there are opportunities in their wastewater treatment plant. Another important recent policies, again, not directly for hydropower, but where there is also hydropower mentioned, is the Social Climate Fund. This fund will support a fair transition toward climate neutrality in order to support also the mitigation of climate change, but also social inclusion, renewable energy, and especially energy community in rural areas. And in this policy, in this document, also the refurbishment of small hydropower plants is eligible. And for example, energy community can rely also on small hydropower. Another important initiative is the water resilience. This will be officially published in a few weeks, but there has been already a consultation process carried out. The scope of the water resilience is to make Europe water resilience, ensuring that water sources are properly managed and scarcity is addressed. And this will also strengthen the competitiveness and innovation of European companies in the water field. This is also valid for hydropower, which is a key topic in the water and energy nexus. In particular, in order to make Europe more water resilient, water storage will be essential. Water storage will include a lot of different strategies, like, for example, managed aquifer recharge, new reservoirs, wetland, but also the refurbishment and optimization of dams, of reservoirs, and hydropower reservoir will be a key strategy. Another project that is running since 4 years is the Clean Energy Technology Observatory, where each year the European Commission publishes a report for each clean energy technology. So one report for photovoltaics, one report for wind, and so on. And there is also one report for hydropower. The last report was published in November 2024, and the 2025 report will be published in November. So November, December, more or less. So I encourage all of you to also read and to give a look at the 2024 report. And I can maybe send the link in the chat. And if you have any comment, any suggestion, any constructive comments, you can send it to me, and maybe we can consider it in the future versions of the release of the report. In this report, we will deal with several topics, not only with energy and power, but also with companies, turnover, employment, and export, import, and so on. So it's a quite complete report on hydropower. Finally, we have the Net Zero Industry Act. It aims at enhancing European manufacturing capacity for net zero technology, so renewable energy technologies, addressing barriers in order to scale production in Europe. And this will allow also to make Europe and the European Union home of clean energy technologies and to be a lead in manufacturing capacity. For hydropower, also this is very important. As you can see in the picture on the left, European Union companies contribute to more or less 42% of all the global export of hydropower equipment. But if we look on the right, we can see the data in yellow that the exports are decreasing over the years. So the aim will be to maintain this export capacity and not to make it reducing. So for example, all the projects that we are hosting today will also be important in this aspect in order to develop new technologies and to make Europe and the European Union a leader in the world in this technology and to maintain a certain export capacity. So just the last slide to inform you about two important conferences. The one will be in October, Hydro 2025, and then there will be also in September in Vienna, the Sustainability in Hydropower, where Daniel, that is our speaker today, will be also the coordinator of the scientific committee. So thank you very much.
Thank you very much, Emanuele. So this is very good information. So there is also good progress in helping to develop more hydropower, let's say, the industry in Europe. And I think that's a very good initiative in general. So, okay, so we go now to the first project. So it's Hydro for you, or Hydro for everybody who is connected to this webinar. So we have Daniel Heiss and Bertrand Alanfi who will present this project. Please go ahead.
Thank you very much. Welcome to our presentation. My name is Bertrand Alanfi. I am the coordinator of the Hydro for You project, working for the Technical University of Munich. And together here with Daniel Heiss from Boku University, who is a freshwater ecologist, who will tell more about the ecological details in our project. And I will start with giving an overview of what we are actually doing here. So please go ahead, Daniel. This is a small overview. We are an innovation action under the EU Horizon program. We have 13 partners in total and a nice budget of 11.5 million euros, of which a large portion is a contribution of the EU. And we are already in the final stage of our project, so we have exactly 1 year left to complete everything. Next, please. We have many objectives, but today I want to point out 2 of them, the main objectives, so to say, and also those we are talking about today. We are developing, demonstrating, and assessing 2 different innovative European small hydropower technologies that I will show for different application ranges. Also, we are developing a GIS-based decision support system, which has the goal to enhance the sustainable exploitation of sustainable hydropower potential in Central Asia. And a few other objectives include that we are looking at climate change scenario analysis. We are developing a water accounting system with the focus on the water, food, energy, climate nexus, which is especially important in the Central Asian context. And of course, we also, what was just said before by Emanuele, we want to support the competitiveness and the market uptake of European suppliers who are competing in the Central Asian market with Chinese technology providers. And therefore, we want to show that European technology is also suitable for this market. And of course, in the range of policymakers, implementers, private project developers, and NGOs, we want to show the key aspects of how to develop sustainable hydropower projects. Next slide, please. So the first technology is the shaft power plant, which is for low head sites. This was developed earlier at my university, and within the Hydro4U project, we have brought it to the next level. We have optimized the modularity, the scalability. Global Hydro Energy, our partner from Austria, has developed a new turbine, which is suitable for this concept. And we have tried to optimize all both static and dynamic elements to improve this concept. And now we are proving it at one of our demo sites. The power output per module can be very small, from 20 kilowatt, but go up to 2 megawatt. And this concept is scalable even for much larger sites, up to, I would say, 10 megawatts, as you can build several modules in parallel to each other. The next technology is the Francis container concept. It's a product of Global Hydro Energy, our partner. Here they have basically put all the technical components, the generator, the cubicles, the turbine, the draft tube, into a very compact steel frame, and this whole equipment fits in a standard shipping container. So the advantage of this is that it can be fully pre-assembled in the factory under controlled circumstances, shipped to the site, and the actual setup and commissioning can go very fast, which is a big advantage for sites that are not so easy to reach or where construction work possibilities are limited. So this is our second technology. It's for a different application range. It's rather for medium heads and lower flows. And the output per container module goes up to 1 megawatt. And it's the same as with the other one. You can put several containers next to each other, which allows scalability. Next slide, please. Yeah, we don't only focus on technologies, but we have also implemented, improved, or also elaborated new methods and tools for sustainable hydro development. Here you can just see a glimpse of our electrofishing team. Daniel will tell more about this later. Next slide. Next slide, please. Yeah, we have also worked a lot with drone surveys. A colleague of mine has developed very nice workflows for really getting very accurate data, which is often hard to get. Here you can see the 3D point cloud of the existing weir structure to which we are attaching these shaft power plants modules in our demo site. So this was all collected by drone survey. The next slide, please. And our hydrology team from Switzerland has put in a lot of effort into climate change impact analysis. So they have set up simulations for our sites of interest and evaluated how the climate change might impact the hydrology at the spots we are looking at. And for example, here you can see a clear shift of the hydrological year as the snow melt goes earlier in the year. So these are things that need to be considered in the design of hydropower plants. Next slide, please. Yeah, now quick glimpse on our two demo sites. The first one, which you saw just the 3D point cloud already, is the Atbashi site in Kyrgyzstan. Here you can see in the background the existing structure. It's an irrigation weir in very bad condition. And with our project, we want to use this existing hydropower potential of around 1.2 megawatt with the shaft power plant concept. Next slide, please. This is how our authority approval design looked like that we developed. So in gray, you can see the existing structures. In green, you can see the new elements. And basically, the idea was to arrange these shaft power plant intakes directly below the weir gates. So they have a double function. They are a hydropower intake structure and at the same time a spillway with a movable gate to ensure the flood safety of the site. Next slide, please. Yeah, here you can see a section through one of our modules. From left to right is the water flow direction. And it's a very simple arrangement. You have a vertical flow deflection at the intake. The water passes the trash rack, which covers this shaft. The gate can be moved vertically up and down to ensure a regulated water level, and which can be fully lowered for flood discharge. And down at the bottom, you see this turbine generator unit, which was specifically developed in our project and gets to be implemented first in this site in Kyrgyzstan. Next slide, please. A short view on the construction works. So this was the progress from last year, September to November. So in just 2 months, a lot of progress could be made already on the construction site. And I think that was it about Atbashi. So there we are now finishing construction works and want to commission the power plant in September of this year. So hopefully on the Hydro conference in fall, we can give a full update on the operational power plant. The next second site is in Shaki Mardan. That's an enclave of Uzbek territory within Kyrgyzstan. And here we are implementing the Francis container concept. We have found a very nice site for it because this was basically a started hydropower project back in the Soviet time, which was abandoned, but some elements were already there, which could be used. For example, the steel penstock of 3 kilometer length was already there, and that saved a lot of time for our demonstration project. You can see the main figures here. So we have 85 meters of head and 2 megawatts of power capacity. Next slide, please. Here, yeah, as I just said, it's some elements were already there, and within our Hydro4U team, our main goals were to develop the power plant in coherence with the European sustainability standards and also quality standards. Therefore, our partners have developed a seasonal ecological flow release plan, as this is a diversion hydropower plant. We have designed fish ladders, both for the intake and at an artificial waterfall in the middle of the diverted stretch. We have developed a guiding rack and a downstream fish bypass to ensure that no fish get into the penstock and harmed in the turbine. And yeah, these were the main elements. And of course, additionally to that, the two containers housing the whole equipment, which I have shown in the beginning. So as I said, these are two totally identical containers, and here we can use the flow of 3 cubic meters per second for the energy generation. A few photos from this site are shown on the next picture. Here you can see the factory assembly in Austria. And here you can really see that everything is pre-assembled and the whole container is put on the truck and brought to site. And on the next slide, we have a few photos from the construction phase. You can see that the bifurcation has been made new, the foundation for the containers, and then the containers just were set on this foundation and the power plant was ready quite fast. So I think that was my part for our presentation, and I hand over to Daniel.
Thank you a lot, Berti. So what we also want to do with the Hydro4U project is also not only to export European hydropower technologies, but also know-how in terms of ecology and sustainability. And what we find in Central Asia is that there's a lot of fundamental and applied knowledge needed. So basically during Soviet times, there was a lot of ecological research happening, but in the last decades, that has basically stood still. To just give you an example, here you see the distribution range of one of our target species, a snow trout. And you see here according to global data, scattered distribution, but where we actually found the species here, a study area, the Shakimadan enclave that Berti just mentioned, the species is missing. So in the sense, we are updating the distribution of certain species. And I want to show you basically, based on the study site of Shakimadan, some of the sustainability assessments and ecological surveys that we are doing. And here is basically showing a communication, a poster actually at the facility to really bring these sustainability concepts on site in Central Asia. So as mentioned, basically we're doing surveys of the distribution and ecology of fish species particularly, but also macroinvertebrates. And our target species is a so-called snow trout, and shown here. And key questions that we're looking at are related to their habitats. So as Berti mentioned, for the e-flows determination, and also looking at snow trout migration patterns, particularly regards to passability assessments. And obviously we're doing pre-post assessments of the hydropower site. What is really key in the Hydro4U project is also capacity building. So we don't only want to do these assessments ourselves, but we want to train the next generation of local ecologists. And as you see here, we're doing some training in electrofishing. And as always, the people are quite curious to see what we are finding here. But we're also training in habitat surveys, biotelemetry, so active and passive. And basically, so we have a few PhD students, also two locals working on that, master students. And for example, electrofishing was not really known in that sense. So we always had to negotiate with the ministry, get special permits to really have this state-of-the-art technique implemented also there for scientific research. We did assessment of fish habitats. So particularly for the snow trout, basically we did microhabitat surveys to delineate where kind of like their preferred suboptimal optimal habitats are in terms of different hydraulic characteristics. These we translated into fuzzy sets rules, and basically in light of consideration of open science, basically we also made this data set available so it can be used for further east, deep, and remote flow habitat studies in different contexts. Regarding fish movements and habitat use, the last years we had a biotelemetry study ongoing where we track the seasonal migration of snow trout, basically. So we caught them, tagged them with active telemetry tags, and then we're tracking them since 2 years now into the project, and that will be crucial to, on the one hand, get basic ecological information, as well as to evaluate then the effectiveness of environmental flow regimes, fish passage facilities. And then we are also intersecting that with apps. So we have a Q-Field app where we basically add the triangulated fish position and be able to study habitat in more detail. So to just give you an overview, an example of how this data looks like. So this is our study site where we have the hydropower plant, and all here, basically you see these fish location points, the fish positions. And we found, so this is one typical fish, a female here that was tagged in the Kokso River in the fall of 2022. The fish remained in the river, and then it moved downstream to the confluence of these two rivers here, so basically the Kokso and the Aksu. There it moved farther downstream towards the Shakimadani to the mainstream, and then the following year in the fall it returns back. So basically what was curious for us to find that this Kokso River, where the hydropower facility is a crucial overwintering habitat because it has warmer groundwater fed flow conditions. So this will be important criteria as we as it informs our assessment and adaptation. You basically see another track of another fish which shows quite the similar pattern regarding to these overwintering habitats here. And in terms of capacity building and dissemination of our work, another thing that is critical is we're doing large-scale GIS assessments, and with that we want to create a web-based application for decision support. So how does this look like, this decision support system? So on the one hand, we're creating a story map and an interactive tool. The story map will serve to communicate relevant region-specific projects results. I won't go further into this now, but the interactive tool, which I want to quickly highlight, will provide the possibility to do site-specific assessments and find suitable locations. So how is this tool, will this be built up? So it will be an online tool where we find spatial information. So shown here, for example, location of existing dams, but we'll also have land use, transmission networks, and so on, combined with a detailed assessment of the river network, basically where you can then zoom in and check out what the discharge, the head, sediment transport is in the reach, and then the user will be able to filter and combine different layers to have their individual assessment and do also different spatial operations, like for example here, intersecting a DEM here. So that is a quick overview. Emmanuel mentioned also, but I want to do a little bit advertisement for this conference here, where you can see more details on our website. I'll share that in the chat now. And with that, thank you very much for your attention, and we'll hand over to the next ones.
Okay, thank you very much. That's a very interesting presentation. I'm impressed about your demo sites, the work which you are doing on site. So you are almost a construction company there, doing everything, not only research. So congratulations, also impressive products which you have prepared. So I would like to mention, Irai already said it, please, if you have questions to the presentation, write it in the chat so that we have then at the end, we have some time for discussing with your questions. So I have a pleasure to present the next speaker, Miroslav Marence. He will present also a very interesting project, Alpheus. I have the pleasure to be there in the scientific advisory board, and I'm looking forward about your presentation, Miro. Thank you.
Thank you, Anton. Thanks for the introduction. Thanks you, Aria, for inviting me here. And I hope I can share my screen. you can see my screen now. Presentation from the beginning. I hope you see it now.
Yes, we see.
I will also move the picture. Yes, I will present the project Alpheus, which is projects dealing with the low head pump storage hydro. In reality, dealing with the we can move to the next. Yes. The Alpheus project is a Horizon 2020 project, which is finished at second part of the last year. And the aim of the project was to improve reversible pump turbine technology and adjacent civil structures which are needed to make pump storage economically valuable in shallow seas and coastal environmental systems where we have a flat topology or topography, better to say. This means we try to find the system how to use pump storage without big heads, which we are used in classical pump storage, several hundred meters to 700 meters in most cases. And these have been done on the level of computational simulations and laboratory experiments, which I will show you later how we make the setup for different turbines. The partners in the project are, we can say, distributed around Europe. Most partners were in the area of the near to the North Sea. Reason for this is because the North Sea looks like ideal position for such power plant system. Today, we can say the pump storage is the most major environmentally friendly method for large-scale energy storage. We can say more than 90% of the electrical energy storage is today done still with pump hydro, and mostly working, as I said, with in the gradients and the areas where we have approximately 250 to 700 meters. And we want to make this method for use in the elevations where we nearly have no elevations, and to use the flat sea as a possible environment for such system. This means the system looks is presented schematically here. We have a flat sea with nearly horizontal, you can say, seabed. And in this seabed, we make the reservoir with the ring dam. In this case, for example, the Earthfield dam. And with changing of the water level in this artificial reservoir, pumping water out, we can pump water out and store it in the surrounding sea, and then use this water for filling of the reservoir and producing additional energy. This was the idea, which then goes into the project. We can say we have, together with coordination, dissemination, explanation work packages, we have one package which deals with turbine design and the power takeoff system, which then they together have been validated in work package 4. Work package 5 is also the work package where I was most of the time working. This is a package which worked with the civil structures and we can say conditions and the challenges which are connected with the building of civil structure of them and hydropower and the power plant, powerhouse. And then the work package 6 made the grid integration and simulations of the connection to the European grid. The first part of the system was to find the suitable locations We checked different countries, especially the countries which were also partners in the project. This means Netherlands, Germany, and France. Also, the Denmark have been checked, but in Denmark we have not found really promising places. And because of that, it was mostly concentrated on these three countries, where the Netherlands, we can say, and the Netherlands coastal area gives the best positions and possibilities for this one. You see here the possible three places in the North Sea, in the, we can say, regional Dutch North Sea. These small dots, what you see, are planned and existing wind parks, which will be built in this area, and we use this, we can say, vicinity to the wind park as a possibility to better also to better produce and better store the wind energy as a not very renewable energy and use it for the peak energy productions. Also, places in the Germany have been found, and also one place in the France have been considered in the project. How these site selection criteria have been done, we have checked the areas. We found out that the possible depth of the sea, which could be reasonable for building of the structures and also for exploitation, will be the sea level between 20, 30, 35 meters. And we tried to see what could be the potential of such sites. We defined two possible solutions. One 200 megawatt plant as a, we can say, starting site and the prototype site, and then the exploitation site of 2 gigawatt, where we see also the storage capacity in the 2 gigawatt hours or 20 gigawatt hours, considering 10 hours of working time. We say the reservoir will be circular, and then we checked also the waves, especially in the Netherlands, as a most far away from coast area, and we found out here on the right side of the diagram, you see the rows of the waves, and you can see from northwest west the waves up to 10 meters are recorded. This means we try to work to make our system resident to the waves of approximately 12 meters. We will see later the two turbine types have been used. Here is the contra-rotating reverse pump turbine shown. Turbine capacity of one machine of approximately 10 megawatt was defined, and this means we need 20 to 200 turbines dependent on the size. Reservoir, of course, must have a big volume and big area. We have this peak with in the smaller solution about 2.2 kilometer diameter, and then to 8 kilometer diameter on the bigger scale. These diagrams you see here, where we have a ring dam around forming the reservoir, and then the area where the powerhouse is situated and the machines are situated. How this cross section look like? Lucky to the position of the North Sea. North Sea seabed is formed with semi-horizontal layers, mostly sandy and clay silty layers, which means in these clay silty layers we have a relatively tight system, and because of that there is maybe a need for the ground curtain just in some special places, and normally we based on the analysis and the data what we have, we can omit the ground curtain, which will reduce also the construction cost of the system. How to build a dam in this rough sea? Of course, this is a big challenge, and several ideas have been followed. At the end, the idea with the concrete caisson forming the dam is found as the most suitable, which means which is on the foundation layer, then connected to the underground with some protection on the seaside, and to achieve the sliding stability and also the stability of the dam structure during the emptying of the reservoir. Inside of the caisson, there is an inner berm which then stabilizes the block in the system. Also, the wave return wall, we can say, known from the concrete face rockfill dams, it will be installed to reduce or eliminate the effect of the high waves on the system. How this caisson construction could look like, of course, we have not prepared these caissons, but such structures are existing. Such structures have been built. They are normally built offshore and then transported with the tugboats or with the semi-submersible vessels on the side, then sink down, similar like it was done with the intake on the Dixons on the Dixons power plant in the Swiss. This is it. The second part was mechanical electrical part. There was a discussion, or there was at the beginning of the project, which types of the turbines could be developed for such systems. Of course, these turbines must be saltwater resistant. 3 systems have been checked. One was the Archimedes screw, which was, we can say, deleted at the beginning of the project because Archimedes screws with length of 10 or more meters are not very reasonable. Because of that, we in the project the aim was to develop the new turbine type, which pump turbine type, or improve it and find it suitable for these conditions. We worked with the positive displacement system and also with the counter-rotating system. The positive displacement system have also been tested in the lab. You see here the efficiency curve, total efficiency curve for such experimental site for the turbining and also for the pumping mode. We can see that efficiency of such system is not very high. We are speaking about 70% in each system. This means the circle efficiency will be relatively low with less than 50%. This was one problem with this positive displacement reverse pump turbine. But the second most problem is that this system is very sensitive on debris in the water, and any gravel sand can easily be jammed, or other debris can be jammed between the lobes and casing, and this was seen as a risk. Because of that, this turbine type was not so followed further. Also, in the test was cavitation and the structural vibrations have been observed, and these were the reasons where we concentrate in the project on the counter-rotating reverse pump turbine. This means we have easily to say something like 2 Kaplan propeller turbines situated one after another and rotating in the different direction. This means if the water comes from left, we can say it's easier, then firstly gives the energy to the rotor 1, which then produce the swirl, and this wheel is used as additional to generate additional energy from this loose part of the swill. And of course, both turbines are rotating in the different directions. Because of that, the disadvantage of the system is that we must have two generators on both sides of the system. This is how the system looked like. This is a testing equipment which was done in the lab of University of Braunschweig. You see here these two turbines installed here, and then with the axis transferring to the generating device or measuring device outside, or generator motor outside of the system. Efficiencies here from the tests are relatively good, we can say. In the test we achieved the efficiencies up to 85%, which makes the system, we can say, attractive, especially if we look at it in the setup that in these systems we have very short power waterways on both sides, just intake and outlet structures after the turbines. Then these hydraulic losses, friction losses can be minimized, and in this way the full cycle efficiency of approximately 70 plus percent could be achieved. Powerhouse design was done on the ideal level, you can say, but here you see the sea outside, reservoir inside, just the short intake part, turbine, and similar system like we use, for example, in the turbines, in the bulk turbines, in the standard hydropower. This means on one side we have a dam structure, then we have a transition section where we come from the dam into the powerhouse section, and then the system of the caissons with the powerhouse, which then also are transported on the side and synced on the right place. Of course, there is an additional problem with the seepage under the dam, which have to be controlled, because the length of the powerhouse module is shorter than the length of the dam section. And also the safety, especially in the large section, we need the safety between the system of the blocks. We must have some, we can say, tightened systems, that in case that some tightening problems happens between caissons, this will be easily located in the system. Of course, when we speak about this, we must also speak about the costs. If we speak about the big solution, 20 gigawatt hours, then and 10 hours operational time of the system with 2 gigawatt power capacity. If we say the system can run 100 years, especially the civil part, and the discount rate of 5%, round trip efficiency, as I said, approximately 70%, and operational maintenance costs defined as a percentage of the capex. We calculated the capex of 5.5 billion euro, which gives at the end the specific costs of approximately 2.75 million euro per megawatt, which is higher than in the case of high head pump storage, but at the same time in this size. But at the same time, we must think about it that we in this area we don't have possibility for high head pump storage. Then it's a question of we can say grid needs and also energy price local. Local cost of storage approximately 190 euro per megawatt hour, which also shows relatively, we can say, effective costs, of course, compared to the conventional pump storage hydropower, slightly higher, but still smaller than, for example, by lithium batteries or by hydrogen at the moment. Also, the global warming potential have been checked. This means CO2 emissions, and also the abiotic depletion potential, which means use of the rare materials, where we can see the effect of this low head pump storage is comparable and really interesting compared to the other technologies, especially if we go into this big size of the storage capacity. This means at the end of the project, we can say that offshore pump storage hydropower is technically, economical, and environmentally feasible. We checked also the turbine on the fish passage. It was not very successful. This means the system will need the screens in front of the turbine, that we will not suck in the fishes and other animals. From the Alpheus project, the official conclusions of the project, the North Sea is a possible site for low head offshore pump storage because of its very flat topo, and also the attractive, we can say, depth of the sea. Civil technologies are already well developed and mature and can be relatively easily be produced. We, for example, were thinking construction just in the summer 6 months, when the roughness and the conditions on the North Sea are much more better than during the winter months. Electromechanical technology have been developed in the model scale and show relatively promising efficiency, up to 80%, 75% of the round trip, or efficiency of 80-85% in the system, total efficiency of more than 70%. Low head offshore pump storage, levelized cost of storage are slightly higher than by the conventional PHS, but lower than, for example, by lithium-ion batteries. Also, global warming potential is similar to the batteries, but much lower by, we have much lower capability of using of the raw metals, and the low head offshore pump storage generate revenues for the grid balancing and time scale from minutes to the days. This part have also been checked in the work package, and especially together with the surrounding wind farms in the North Sea. This could be very good system to improve the value of the wind energy in the European electrical grid. So thank you, and we'll be happy to answer your questions.
Thank you very much, Miro. A reminder to all, please write your questions you may have in the chat. So I think that's a very nice and interesting concept, is offshore pump storage. You mentioned it, close to wind farms. Of course, you can also take into account, you can save grid reinforcement because you are using closely this storage. So I think that's can be also counted when it comes then to economical evaluation. So thanks a lot, Miro. So we we have last presentation. So we have the project Hypos, and Karin Schenk will present us this project. Please go ahead, Karin.
Thank you very much, Anton. I think you now see my slides in a minute in presentation mode, I hope.
No, just the present. Yeah, perfect.
Perfect. Good. Yeah. So I'm going to talk about the Hypos project, the hydropower suite, which we call it. So supporting hydropower from space. And yeah, my name is Karin Schenk. I'm the EO service line manager at EOMAP, a Foucault company. So let's start. So Hypos project was a EU-funded project from 2019 to 2022. So we had 5 partners. We lead the whole project. And we had also Stucky, now Gruner, who is this engineering and design company from Switzerland. We had the Swedish Meteorological and Hydrological Institute, SMHI, for the hydrological modeling part. And our partner from Norway, so NTNU, were the in situ and three-dimensional modeling experts. And for the calibration and validation activities, the partners from CNR in Milano were part of the project. So what was it about? The concept was that we include satellite data and drone data, hydrological modeling, in situ data and field monitoring, and also market capacity assessments into an online dashboard, which is cost efficient and easy accessible for different stakeholders and can produce data worldwide. So this should improve and support hydropower in its design and planning phases, but also in the operation phases. So we have a final product, which with a nice logo here, which you can access. I can show you later again on the registration site. So let's dive deeper into the portfolio. So what we had developed here was first an operational monitoring of reservoirs and river systems by satellites, then also near real-time hydrological and sediment state analysis, and also a near real-time monitoring of sediment management activities and baseline environmental information. So I will give for each of them an example in the next slides so that it makes some more sense. So first, the operational monitoring of reservoirs and river system. So everything was here EO, so Earth observation, which means satellite mainly monitoring of basic water quality parameters, including turbidity and sediment concentration on a regular basis, which is delivered through this EO Hypos. So here we had one example here in Banja, Albania, a reservoir built in 2016, where we used different satellites from the Copernicus. So this is an EU program. The Copernicus satellites here, Sentinel-2 in 10 meters, which records this area about every 5 days, but also complement this information with USGS NASA missions Landsat 7 and 8. Now there's another one, 9, but in this project phase, we only use 7 and 8, which is a sensor which monitors in 30-meter resolution and every 8-day revisit time. So here you see, for example, some time series. So we analyzed different years, so 2017 to 2022 for different parameters. Quite wild graph with a lot of colors, but you see, for example, the water temperature with a nice seasonal variation, and also the executive depth, so the visibility, the chlorophyll A, which is a proxy for algal blooms, and also the turbidity, which can also be translated into sediment concentrations. So this is another visualization of this Banja use case with a nice RGB. So this is a turbidity map in this case from the 18th of October 2022. You see that we have an inflow from the south of the rivers and then the dam in the north west. So what you see here is the time series. What's quite distinctive here is this feature. So actually at this part, there was the dam construction started. So we see before a quite high turbidity level at the point. So the point was actually here. And then it flattens, of course, after the dam construction. So this can be assessed worldwide. So it's quite interesting for the monitoring of the sedimentation here. Another example here, what we also do since 2020, 2020 is another hydropower reservoir which we monitor, which is Caorabassa in Mozambique, quite large reservoir. And here we use different satellite sensors, also from the Copernicus satellite fleet. Here we, in addition to Sentinel-2, also use Sentinel-3, which is much coarser in 300-meter pixel resolution, but it comes up to daily, so we have a much higher data frequency. And also, as I mentioned before, we use here the different Landsat missions 7, 8, and 9. Yeah, you see here some nice time series again. So here, one station in the west and one station in the east, and you see already the differences in this case, the turbidity from one station from the inflow, and here that's in the middle of the reservoir in yellow. So the next one would be the near real-time hydrological and sediment states, so up-to-date reporting on flows and sediment concentration provided by the modeling part. So here we used the SMHI models of the worldwide HYPE and localized it. And here we have different parameters. For example, in this current stage of the worldwide HYPE, there was river discharge, precipitation, specific runoff, mean temperature, potential evapotranspiration, and actual evapotranspiration. So you see here also a nice time series of, in this case, discharge at different stations, again from the outflow and further towards the dam. Another one is the near real-time monitoring of sediment management activities. So here we specifically targeted data acquisition with very high resolution satellites to help analyze fast dynamics on single events. Our use case here was the flushing at the Rhone, south of Geneva, so at the Chancy-Verbois and Genisat river plant installation. So here we use the Planet Super Doves in 3-meter resolution. They can have up to several times daily frequency. And you see here an example of the whole cascading river installation set. So from the north with the Verbois over to Genisat in the southern region. And here you see 2 different dates. So that was 27, there was the flushing taking place. And on 29 already, the flushing has been ended and it filled up again with the water. So for this, you can analyze the turbidity very detailed in the river branches from satellites. So everything is remote. We don't have to go on site. So to get information for all parts of the Rhone and its tributaries, you can assess the representativeness of in situ measurement locations and also save costs by reduction of in situ measurements needed. So you can place the sensors at a specific location where there, for example, in the historic baseline, were already some increased values reported. Another one is the baseline information on environmental data. So here we have currently, actually, so HYPOS was an EU-funded project, but we also continue the research here in this field. So we have a pilot project performed for the World Bank in the framework of the ESA's GDA program, so for global development edition or something. I don't know. Remember the extreme abbreviation. And we here had 3 different reservoirs in Peru, Lacto, Cameroon, and Buechos. And we analyzed here the sediments in this reservoir. And here you see the time series from 1981 until 2022. And you see that the almost 50% of the total sediments comes from 2 of the El Nino years, so 1983 and 1980 and 1998. We also analyzed the seasonal patterns. Here you see the months, so that we have a peak in these months from August to October. So relatively new, also another project which we have right now running. It's about snow data, so snow data addition into HYPOS, especially snow depth and snow water equivalent. So you see here this nice graphics. So we are looking from satellite-based area-wide snow depth and snow water equivalent data information. So this is also an ESA project, which is currently running until 2006. And the application is to optimize hydropower operation, assist with flood forecasting, estimate freshwater resources, and also help to plan water utilization from local to regional scales. So we use here SENHIL-1, so it's a radar sensor, but also meteorological forcing data, and this is all processed with this SNOWCAP processor. So here there's a company included as partner, and we as EOMAP provide the HYPOS portal to have the data visualized. For example, we have a pilot user, which is Enel, who uses the data, and this is an example of snow data in Italy. In this case, the snow depths. You see here already a time series, so two different snow depth information. One is monthly, and the other one are the single measurements created. So I'm already finished. I'm quite fast. So you can also register at our EOP HYPOS with some demo data. And of course, you can reach out to me if you have any questions. Thank you very much for your attention.
Thanks a lot, Karin, for the nice presentation. So you showed very innovative monitoring approaches using remote sensing. So I think that's important for hydropower, and you showed already very interesting application which are ongoing. So we have a few minutes time for questions. Not to lose too much, I go from the back. So from Barbara, we have a question about European sustainability standard. Is it aligned with the global hydropower sustainability standard? I think that's for Emanuele.
I will try to give some hint. Thank you, Barbara. I suppose that this question was written during the presentation of Hydro4U because they mentioned some standards.
Okay.
Yeah, but I can also give a hint. Yeah, in the European Union now there is the taxonomy of sustainable investment. There is also a hydropower part where there are some criteria to define an investment in hydropower sustainable or not. And these are quite general criteria, like, for example, the power density should be above a certain limit, the carbon emission per kilowatt hour should be below a certain limits. And these are very general guidelines. The Global Hydropower Sustainability Standard, I think you mean the one then developed by the International Hydropower Association. This is very site-specific for each hydropower plants, while the European Commission gives more general view. So I think that should be the opposite, not that very specific assessment should be in line with general criteria of the European Commission.
Okay, thanks a lot. I see the next question from...
maybe Ento, maybe also the Bertrand or Daniel can add something.
Yes, I can add something shortly. So I was referring to this phrase, European sustainability standards, rather in the context with the Water Framework Directive, and also what you just mentioned, the IHA's Global Hydropower Sustainability Standard. So it's not like one specific standard we were following, but in general, sustainability standards that are commonly applied in European countries, and also here in Europe from country to country. It's different because it goes into national legislation. The framework directive is, as it says, just a framework directive. So we are generally trying to keep a high level of sustainability compliance that is usually also done in European countries, to say it in a simple way.
Okay, thank you. I think for Hydro4U is also a question of Professor Arun Kumar. Interesting layout for vertical turbine. By the way, do you need to have a gearbox? What is type of generator and how to adjust water variations?
So I'm not sure which turbine Professor Kumar is referring to, because both turbines that we showed have a horizontal axis. And for the shaft hydropower plant turbine, this so-called Kaplan Evo turbine, there is no gearbox. The generator is directly attached to the turbine runner. It's similar to the earlier Straflo concept. So the generator rotor is housed so the magnets are housed in the outer runner of the turbine, and there is a small gap between a water-filled gap between runner and rotor and stator, and therefore this concept is very compact. There is no gearbox or anything. And the other concept, the Francis container, I have to admit that I don't know if it's exclusively without the gearbox, but the one in Shaki Mardan is without the gearbox. It's directly coupled to the generator, and the flow variations in both concepts are regulated by adjustable guide wings.
Yeah, then the other question I see here from GP Person, can you give us an order of magnitude for construction cost per megawatt? How does it compare with more conventional technologies? So that I think that depends now the shaft powerhouse or the
absolutely
the Francis turbine box.
And it also depends a lot on the specific site and the site parameters, especially the head and flow combination. So if you build a shaft power plant of this type at 2-meter heads with 20 cubic meters per second, or 8-meter head and 10 cubic meters per second, the cost per installed power will be very different. And therefore, I cannot give a general answer to this. But I can let you know that the power plant in Kyrgyzstan, which we are building, has total project costs for the 1.2 megawatt between 3.5 to 4 million euros.
Okay, thank you. Just a question from my side. This construction cost, I guess they were not included in the project budget. Okay.
No. We have the budget covered for the development and manufacturing of the technical equipment. So that's the turbine and the hydraulic steelworks, which are made by our partners. And the local construction costs are done by a local future operator of this power plant, who is not a consortium partner, but we have a separate agreement with him. And he covers all the local project costs, including the concrete works and so on. And in turn, after the Hydro4U project ends, he will get legally the owner of the whole power plant.
Okay. Interesting construction of the consortium. That's interesting. Next question go from Alterach Julio Alberto. A question for Miro. How should pumping and turbining operation be managed when the reservoir is at an elevation close to the sea level? What is the minimum safe operation level? Because of cavitation, I don't read more.
Yes, I read the question. Thanks.
Okay.
Thanks, Anton. I will try to answer it. We make the tests and also numerical simulations, CFD simulations, for the variation of the reservoir level operation in the reservoir level from -2 to -15 meters. This means the existing contra-rotating turbine could work with relatively good efficiency in full this range, or global efficiency above 70% in all this in this range. And in this range, there was no cavitation problems, because one of the ideas from the civil part was not to build to install the turbine deeper than the seabed level, to install the turbine above seabed level. On this way, we cannot use the full reservoir depth. We just use the upper, we can say upper labella of the system, and the rest of the water in the reservoir is in reality the covering of the turbine for against the cavitation.
Okay, thank you. I have just also a question. You mentioned about screen. Where you do a screen to avoid that you pump in out, let's say, any floating debris, but of course also fish or fish eggs or any other invertebrates or crabs and so on.
this is something which stayed open for the next stage of the project. It is because we have to pump in enormous amount of water. We have very high discharges through the turbines, and this will need relatively big screens to solve the problem with not sucking the debris and also the animals. This means also the screen must be very small size, and this is something which have to be discussed together with the problems with algs and other shells, which can be also then we can say cloak these structures. How to make the screen cleaning systems and so on. This was also discussed in the project. I have not presented it here, but on the level of TRL, I will say, in my opinion, TRL 5 to 6. It's far away from implementation, but the problem have been detected and discussed.
Yeah, there is some experience with so-called smalt screens, which are in Scotland for pump storage, so very fine screen, but of course they are located very far from the intake. So that's a certain kind of a solution. I see Himanshu Jain. What is the scope for power electronics related research in pump storage, hydropower? I don't know who would like to answer that question, which is, I think, more general. Perhaps not so clear. Yeah. Okay, we will see if we can answer perhaps online. Then we have a question for Karin, again from Julio Alberto. Was a calibration phase of the satellite data required to measure sediment concentration, and what kind of instruments did you use for the measurements?
Yeah, very good question. So in principle, so from the satellites, you get a backscatter signal. So to transfer this into sediment concentrations, we used in situ data from different measurements. So for Banya, there was a fixed station with an acoustic Doppler focal station. Then we had also laboratory analysis. So we so the partner CNR took laboratory samples and gravimetrically weighted the sediment concentrations. And also we used for the ARF openly available data by the Swiss government on turbidity, and also for the Rhone, for the flushing event, we had from the providers the data provided for the sediment concentration at different stations.
Okay.
They're also CNR, but not CNR from Italy, but from France, actually.
Ist das jetzt gemacht?
Okay, thank you. I see on the top another question.
Das lässt laufen, da.
Okay.
Du ja.
Das sagst du Namen vielleicht. Ja, gut.
I think someone has the microphone.
There is another question around ongoing in parallel, I think. There is another question, Miro, for you. From Professor Arun Kumar, saying that it's an interesting concept. Question regarding choice of dam materials. Is any report available publicly?
So thanks Anton. There is somebody speaking parallelly, but I hope you can hear me.
We cannot find out who is it. So
who is it?
I cannot find any microphone.
Me neither.
We can say on this way. The material which is used, this was one of the ideas. We want to use the original material which we can find on the seabed. This means of course the caisson is built of concrete, but other materials which are used for the berm, inside berm, will be in reality the dredged material from the seabed in the inside of the reservoir. And for the other parts, for example, foundation and so on, this material must be prepared offshore and then brought to and installed on the area. Any report of the project in the public domain, the most reports are visible, and I can put the web page, because in meantime I opened the web page. I can try to put it in. Yes, I put it on the same size on the same place where the Professor Kumar question was. I hope you can see it now. Yes, it's in the chat.
Okay, thank you very much, Miro. So I think we are coming to the end. It's 3:00 and 1 minute. So
Anton, sorry,
yes.
there are also other 3 questions, but that are hidden because they are posted not as question, but as comment to the Barbara question.
Okay.
So if you want, I can read them. From Matteo Vicentini, I think, to a question to Miro. Is low head pump storage intended to deal with salty water? I think.
Of course, it is. Yes, because it's in the North Sea.
And is the efficiency supposed to deal with a very variable head?
Yes, as I said, we tested it in the head from 2 to 15 meters.
Another question by Jean-Jacques. In the LCOE presented by Miro, the cost of dam is crucial. Have you considered technical uncertainty which impact the LCOE?
Yes, we discussed this caisson building also with the companies which are doing it, which are making the caisson solutions, and on this way it should be the possibility. What is unclear, we have made the analysis of both. If the caisson is filled with water, there is a simpler system. Then you just flooded it. And if you make it, if you have to fill it with the sand because of stability, then of course will be needed to have some openings where you can do it. But the caissons are relatively simple because they have a simple tightening system. The tightening will be more crucial and more critical in the between the 2 caissons for the powerhouse area, we can say.
Okay, I don't see any other questions.
Is that
yes, I think I see. Of course, we will share all presentations as normally, so they will be available. And I think okay, then we can close this webinar. We would like to thank all the presenters for this very informative and interesting presentations, and also the audience for participating, quite numerous. So I've seen we have past 70, 80 sometimes during this webinar, which is very good. Thank you very much for the participation, and thanks, Rayo, again for the organization, all the technical matters which you have prepared. And I think we will come soon with another invitation for another webinar, 6.1 of this boosting hydropower best practice for research. So thanks a lot for everybody participating, and have a nice afternoon, and have a good life with hydropower for you. Thank you very much.
Thank you, Anton. Thank you, Raya, and thank you all for the questions. Bye.
Bye-bye. Bye.
Bye.
Thank you.
Bye-bye.